4 pi r squared gives you the surface area of a sphere. But where does the formula come from? First, we'll create a sphere and fill in its surface area. Next, we inscribe a polygon inside the sphere, and we rotate the polygon along its horizontal axis to create a 3D model. Now, if we increase the number of sides of the inscribed polygon, we can see how this affects the shape of the model. Specifically, notice how the surface area of the model approximates the surface area of the sphere. So if we increase the sides of the inscribed polygon to infinitely many sides, then the surface area of the model becomes equal to the surface area of the sphere. So let's derive a formula for the surface area of a model where the inscribed polygon has an arbitrary number of sides. We can see that the model is made up of 2 cones at both ends, and in the middle we have shapes called frustrums. In order to find the surface area of the model, we need to find the surface area of the cones and frustrums without their bases. First, the surface area of a cone without its base is equal to pi times the radius times the lateral height. And the surface area of a frustrum without its top and bottom bases is equal to pi times the radius of the top base plus the radius of the bottom base times the lateral height. Next, let's take a 2-dimensional view of our shape, and we can see the equilateral polygon that is inscribed inside the sphere. We will label the vertices with capital letters, and we label all the sides with the letter S. Next, we need to point out some unique properties related to an even-sided equilateral polygon. First, the vertical lines that connect the opposite vertices are parallel. And the same is true if we connect points CH and DG, which are parallel with lines AB and EF. Another property is that the horizontal line AE intersects the vertical lines at right angles. And there are multiple diagonals that form right angles with the sides of the polygon. One final property is that line AE is a diameter which bisects the polygon. Therefore, if we label this line as R1, then the line below also has length R1. We label the next line R2, and the last line we label as R3. Now, as we can see, the polygon is made up of different sized triangles. Before we can find the surface area, we must first establish an important relationship between these triangles. First, we label the intersection points in the middle, and let's look at triangle ABI and HIJ. The vertical angles formed by both triangles are equal. And since line AB is parallel to line CH, the alternate interior angles are equal. Since both triangles have side R1 in common, then by the angle-side-angle theorem, both triangles are congruent. Therefore, all the corresponding angles are equal, and if we call this side of the triangle D1, then the corresponding side of the other triangle must also be D1. Next, let's look at these 2 triangles. The vertical angles are equal, and since line BH is parallel to line CG, the alternate interior angles are equal. Notice that both triangles have all the same angles. If at least 2 angles of one triangle are equal to 2 angles of another triangle, then both triangles must be similar. In the same way, we can show that the following triangles are also similar. Next, we need to point out that these pairs of triangles are congruent by the angle-side-angle theorem, so they have side D2 in common. And the same is true with these pairs of triangles, which have side D3 in common. Finally, we will look at this last triangle, and it is also similar because it has 2 of the same angles shared by all the other similar triangles. Since all these triangles are similar, we can establish an important relationship between them. Specifically, we will show that the corresponding sides are all in the same proportion. Therefore, R1 over D1 is equal to R2 over D2, which is equal to R3 over D3, which is equal to line AD over S. Next, we will cross multiply each of these terms, so we have R1s is equal to D1AD, R2s is equal to D2AD, and R3s is equal to D3AD. Next, we will add these equations together, and we have R1s plus R2s plus R3s is equal to D1AD plus D2AD plus D3AD. On the left-hand side, we can factor out and divide by s. And on the right-hand side, we will factor out line AD. So let's take a look at what D1 plus D2 plus D3 actually represents. We can see that these are line segments that form the diameter AE. So let's arrange the segments around. And we can see that D1 plus D2 plus D3 is equal to half of line AE. Therefore, R1 plus R2 plus R3 is equal to line AE times line AD over 2s. Finally, this is the important equation we need as a result of the similar triangles. We can now begin to find the surface area of the model by finding the surface area of the cones and frustrums without their bases. So the surface area of the model is equal to the surface area of the first cone, which is pi times R1 times s, plus the surface area of the first frustrum, which is pi times R1 plus R2 times s, plus the surface area of the second frustrum, which is pi times R2 plus R3 times s, plus the surface area of the second cone, which is pi times R3 times s. Next, we will use algebra and factor out pi, and we will also factor out s. We can then simplify further by combining like terms, and we will factor out the 2's. Therefore, the surface area of the model is equal to 2 pi s times R1 plus R2 plus R3. Now notice that R1 plus R2 plus R3 is the equation we derived as a result of the similar triangles. Therefore, the surface area of the model becomes equal to 2 pi s times line AE times line AD over 2s. The 2's cancel out, and the s's also cancel out. So the surface area of the model is now equal to pi times line AE times line AD. Next, let's focus on line AE. And in terms of our sphere, line AE is the diameter, and the diameter is equal to twice the radius of the sphere. Therefore, line AE is equal to 2r. Next, let's look at line AD. So what we are going to do is increase the number of sides of the inscribed polygon, and let's look at what happens to line AD. As we can see, line AD begins to approach the diameter. So now we are going to increase the sides of the inscribed polygon to infinitely many sides, and the first thing we should point out is that the surface area of the model becomes equal to the surface area of the sphere. The second thing is that line AD eventually becomes equal to the diameter, which is equal to 2r. Finally, the surface area of the sphere is equal to 2 pi r times 2r, which simplifies to 4 pi r squared. Therefore, 4 pi r squared gives you the surface area of any sized sphere that exists.
4 over 3 pi r cubed gives you the volume of a sphere. But where does the formula come from?
1 over 3 area of the base times height gives you the volume of a square pyramid. But where does the formula come from?